Hey, good afternoon, everyone. My name is Tom Douglas. I'm with RACO. Thank you for joining us today. We've got probably a large group on. This has been a hot topic right now, discussing a little of the new silica rule, or the new OSHA silica rule, rather. Leading our seminar today is Ron Roberson from Sensidyne. Many of you out there probably know Ron. He's been in the industry for a long time. He's got over 40 years experience, and I think well, just short of, you're a little over 30 years at Sensidyne as well. Is that correct, Ron?
Yeah, 32.
32, all right. And he's active in a number of organizations, AIHA, ASTM, American Chemical Society, ACGIH. So he's a pretty good resource here. So we really appreciate him taking the time to walk us through a few things that probably on everyone's mind. Hey, how I'm going to deal with this new silica standard. Couple housekeeping items. We will be doing a recording of this webinar, so if you jump in late or you wanted to share it with somebody or watch it at a later time, we'll make that available at our RACO training page. We'll also have the slide deck available to you as well, so if there's some things there that are of interest, we'll have access to that. We do have a large group, and we're going to try to get every question that comes through. Everyone on their pane, kind of on the right-hand side of their screen, they should have an area that says questions. So feel free to type things as we go along. We may try to get to them during the presentation, but chances are we'll probably address all of them at the end. Any other questions or problems, yeah, feel free to send through the questions or chat, and I'll do my best to address those. So without further ado, I'm going to send it over to you, Ron. Again, appreciate the time, and the floor is yours.
Thank you, Tom. I appreciate it very much, and I'd like to welcome everybody. It's a beautiful afternoon here in Florida. I hope it's equally nice wherever you are. Today we're going to be talking about the silica standard, specifically the air sampling portion of it, and what we have to do in order to comply with this new standard. It's a little bit different from anything else that they've given us in the past, in that there's we're not tied to a flow rate like you are with most methods, and we'll get into that as we go. But that's our subject today: the personal air sampling for crystalline silica exposure, especially as applied to the new standard. Basically, we'll start with a quick overview of the standard, and I don't pretend to be an expert on it. My expertise does lie in air sampling and not in every little comma and period with this standard, so please bear with me. But what we're looking at is that the standard became effective basically last week, June 23rd. The new PEL is 50 micrograms per cubic meter for an 8-hour time-weighted average. Employers under this standard must provide engineering controls to assure that the exposure is at the PEL or lower. Well, you know, how do you know that? Well, you have to sample, and that's why we're here today. Employers must also provide personal protective equipment, particularly respirators, whenever the engineering controls are inadequate. And again, how do we know that? We know it by air sampling. Employers must also provide medical screening and training with this standard. Compliance for the standard, the construction industry has 1 year, 6/23/17, they need to be up and running with this. General industry has 2 years out to 2018. Compliance for fracking, they're giving them 5 years for engineering controls and then 2 years for everything else, that being overcoming the problems of engineering controls at a fracking operation. And the next thing we want to talk about is air sampling is covered under Appendix A. I'm going to talk about Appendix A a little bit later. First, I'd like to do some background information just on historical sampling and how we came about where we're headed today. Traditionally, we've followed one of these methods as an industrial hygienist. If you've been around a while, you've probably done one of these. NIOSH 7500, 7601, and 7602, all crystalline silica methods that are very, very similar in the field sampling. The main difference between them is in the laboratory analysis, where 7500 uses X-ray diffraction, 7601 used visible spectrophotometry, and 7602 used infrared spectrophotometry. We also had OSHA ID 142, which was very, very similar to NIOSH 7500. In these methods, they were all originally written around the old Dorr-Oliver cyclone, and then some of these later cyclones have been added to them as they've been updated. But the Dorr-Oliver cyclone is the one in the center, shown in the center in this slide. You probably all will recognize it. It's nylon 10 millimeter cyclone. It operates at 1.7 liters per minute. It dates back to the early 1960s. I think about 1962, the Bureau of Mines began to use it in coal mines. Prior to that, in coal mines, they collected samples, dust samples in an impinger, actually an midget impinger, which had been invented in the late 30s, about 1937. And they started the sampling in the 30s with a hand-operated pump, had a big crank on the side of it, and it was actually operated by a second person who followed the miner around. In the 50s, about 1957, they got their first motorized pump, and then in around 1962, they went from impingers to this cyclone. So there's a whole lot of technical information around. Lots and lots of papers have been written on this, on the Dorr-Oliver cyclone, and there's a ton of data around that was collected with that cyclone. The Higgins cyclone came along a little while later from the UK, and it operates at 2.2 liters a minute. The unique thing about this cyclone was that it had an inlet connection. I'm going to talk more about this in a little bit, but the old Dorr-Oliver had no hose connection on the inlet. And then sometime later also, this cyclone shown in the upper right part of this picture has it came along operating at 2.5 liters a minute. It was simply known as the aluminum cyclone. And those three, or some combination of them, are written into all those the standards that we just talked about that we've used for years. And you could use most any personal pump that would do 3 liters a minute or up to 5 liters a minute. But it was imperative to use a pump that has constant flow control that will maintain the flow rate within 5% of where you set it. Constant flow control in these pumps works like cruise control in a car. You set the flow rate. As the back pressure changes, as you load the filter up, it will sense that, and it will speed up the motor and maintain the flow rate. Most every personal monitoring pump today on the market has this feature. There are some low-cost pumps that are designed mainly for the asbestos abatement industry that don't have it. So you want to make sure that any pump you use with a cyclone has got constant flow control, because it's imperative that you hold the flow rate steady to get the proper size cut. The old Dorr-Oliver cyclone, I mentioned it did not have a hose connection on the inlet. The way we got around this traditionally when it came time to calibrate it was to put it down into a gas-tight jar, and the jar would have 2 connections on it, so you could make the inlet connection, and as this diagram shows, you could calibrate the system. I will mention that both OSHA and MSHA have allowed a variance to this method. They allow you to take the filter cassette out of the cyclone and just put it in line, so you don't have to use the jar. And there are different schools of thought about this. I'm an old school guy. I like to calibrate something exactly the way it's going to be used in the field. If you remove the cassette and sample without the cyclone, you're assuming that the cyclone itself has no back pressure, and I don't think that's exactly a true assumption. So I would rather use the jar, calibrate it the way it's going to go out in the field, just make sure that the jar is airtight. And you could do that. You could run a quick test on it just by pinching the tube between the calibrator and the jar, pinching it shut, and that should cause the pump to stall. If it doesn't, then that means you got a leak somewhere. At any rate, as we looked at this Higgins Duel, and a lot of the other cyclones we're going to talk about today have got an inlet fitting, and so that does eliminate the need for that calibration jar. What we're showing here is a particle size distribution curve. The solid blue line is the distribution curve that's recognized in the U.S. It's known today as the ACGIH curve, and this is basically what the human body does as far as the particle size penetration from particles that are, say, below 2 microns in size. Pretty much 100% of them get to the lungs. When you get up to particles that are above 8, say 8 to 10, almost all of them are knocked out by the upper respiratory tract, and things bigger than 10 microns don't enter the body at all. They are knocked out by the upper respiratory tract. But the rest of the sizing follows this gradual curve, this ratio that's involved in it, and the 50% point is at 4 microns, according to this theoretical curve. The dotted curve here that we have in red shows the fit that you have with the standard Dor-Oliver cyclone at 1.7 liters a minute. It fits that pretty well, and all the cyclones I'm going to talk about today will have a similar fit around this curve if you operate them at the correct flow rate. Now, this is extremely important to understand that there is a specific flow rate with a cyclone to give you this particular curve. And in Europe, they follow a similar curve, but they operate the same cyclones at a slower flow rate, and it shifts the curve to the right so that the 50% cut point is at 5 microns and not at 4. And that's just the convention they follow over there. It's called the BMRC curve. I think that's British Medical Resource Council or something like that. It's a BMRC curve that they follow in Europe. So many cyclones that are on the market today are sold globally, and they will have 2 different respirable flow rates assigned to them. One is for the U.S. and one is for Europe. And so you got to make sure that you're following the correct one. But watch the instructions and make sure you're getting the particle size distribution that you want, which in North America is going to be this one here, what's known as the ACGIH curve with the 50% cut at 4 microns. When this standard first became an issue with OSHA, which was about 7 or 8 years ago, when they first started talking about it, NIOSH began to test some higher flow rate cyclones in anticipation of the PEL being lowered. And they figured that they were going to have to go to some higher flow rates in order to get the sensitivity down to meet the new standard. They began testing higher flow rate cyclones, and these are some that were tested at NIOSH. The first one I want to talk about is the one on the left here. It's known as the GK 2.69. It operates at 4.2 liters a minute and uses a standard NIOSH style cassette, 37 millimeter, like we've always used. Nice and lightweight, and you see it more than doubles the flow rate of a Dor-Oliver, but it basically doubles the flow rate of the original cyclones that we talked about, that the older standards were written around. They also tested this GK 4.162 called the Rascal, which I think stands for Respirable Air Sampling Cyclone Aluminum Large, I think is what that stands for. The inventor went to some real trouble to get the word Rascal out of that. But anyway, that one operates at 9 liters a minute. It actually has a pretty good fit at 8.5 and a pretty good fit at 9.5 to that curve, but it operates best at 9 liters a minute. And these photos in this slide here are not to scale. That cyclone is shown in the center there, and it's quite a bit larger than the one on the left in real life and quite a bit heavier. The third cyclone shown down in the lower right-hand corner is one that was developed in Germany. It's called the FSP-10. It operates at the European particle size distribution curve at 10 liters a minute, and in the U.S. it would have to be used at 11.2 to meet our curve. And it is also quite big and quite heavy. It's another one they tested. You'll find very few of those in the U.S. They use a cassette that's pretty much unique to Germany, but that is another one of the ones that they tested, and they are available in the U.S. as well. There were at least 3 papers written that I'm aware of on these on the testing that NIOSH did of these high flow rate cyclones, and they're listed here. The first one that's listed there came out in 2010. Another one in 2011. The one down at the bottom that we showed their evaluation of the penetration characteristics, that one that testing was actually done in the UK under contract for NIOSH. But all 3 of those are testing these high flow rate cyclones, and basically these are the verifications of those cyclones. And these papers are all readily available. You can get them, you can find them on the internet. Now, what we have available from Gillian is in the way of cyclones is listed in this table here. And I'd just like to point out a few things about these cyclones. The Dore Oliver cyclone, construction materials nylon. Look at the weight, if you will, the approximate weight in kilograms, 0.08 kilograms. It's quite lightweight. And of course, as I mentioned, it follows the ACGIH curve at 1.7 liters a minute. Then the next 2 that we have 2 versions of the Higgins Duell cyclone. One that accepts the US style cassette, NIOSH style cassette, and the other one that accepts a European, actually that German cassette. And they're both, if you look at the weights there, 0.15 and 0.14, they weigh about twice what the old Dore Oliver weighed, and they operate at 2.2 liters a minute in the U.S. Okay. If you look down at the medium flow cyclone that operates at 4.2 liters a minute, look at the weight on it, 0.12 kilograms. It's almost as light as the Dore Oliver, and considerably lighter than the Higgins Duell, and it operates at 4.2 liters a minute. This is a very good choice for collecting a larger sample because it is lightweight. There's a lot better wear acceptance with it. If we get down one more line here to this Rascal cyclone that works at 9 liters a minute, now look at the weight, 0.26 kilograms, and it's the same with this FSP-10 out of Germany. They're quite heavy. That's 3 times the weight of the nylon cyclones, and they are quite big and bulky. And when NIOSH tested these, they got a lot of complaints on those 2 cyclones from the people that had to wear them. So just keep that in mind, that there are times you have to go to those cyclones, but you don't have to use them all the time. And if you can get by without them, it's best to stay with the lower flow cyclones. And that medium flow cyclone is a very good choice. And I'll explain that further as we go here. Sensidyne did come out with 2 new pumps. In anticipation of this standard, we have a 10-liter pump called the Gillian 10i that goes from 4 liters a minute up to 10. Very good back pressure capability and does have an intrinsic safety approval. And we built this pump on the platform of the Gillian 5000, which has been around for a while. So it has the same 4-button interface and has start-stop programmability and nice digital readout of flow and all that. So it's not a super heavy pump to wear for that nice high flow rate range. And in all fairness, there are some other companies too that have pumps in this same flow rate range that you can sample up to 10 liters a minute. We also came out with a Gillian 12, which will go to 12 liters a minute. It's very similar in format, very high back pressure capability, but it does not have an intrinsic safety approval at this time. That's something that we're working on, but we don't have it right now. But just keep in mind that those two pumps are available for these higher flow rate cyclones. And I'll talk more on that as we progress. Now this brings us up to Appendix A. This is a two-page document that is part of the standard, and it's the part of the standard that addresses the air sampling. And so we need to pay attention to what it says, because this is where basically all of our information comes from for the air sampling. Basically, it says this appendix specifies the procedures for analyzing air samples for respirable crystalline silica, as well as the quality control procedures that employers must ensure that laboratories use when performing an analysis required under 29 CFR 19.26.1153 D2 and Roman numeral 5. What this tells us, it's specifying particular procedures, and it's going to list 6 methods that we have used traditionally. But if you look at this last line down there, it makes a statement that you can optimize the methods and the instruments to obtain a quantitative limit of detection that represents a value no higher than 25% of the PEL based on sample air volume. Okay, what does this tell us? It doesn't give us a flow rate like all the other 1,000 NIOSH methods do. It doesn't tie us to one particular cyclone, but it says that we can optimize these 6 methods. Now let's look at those. These are the 6 methods that are listed in the silica standard. OSHA ID 142, NIOSH 7500, NIOSH 7602, 7603, and 2 MSHA methods, P2 and P7. And you will see by the analysis methods that they allow X-ray diffraction and infrared spectrophotometry. The old visible method was not picked up. The visible spectrophotometry method that NIOSH had is not listed here. So OSHA wants us to use either X-ray diffraction or infrared spectrophotometry. And it has listed these 6 samples. And all of these were originally written around the Dorr-Oliver cyclone. Okay, some of them also allow the Higgins Duell, and some of them allow the aluminum cyclone, but they were all written around approximately 2 liters a minute with the various flow rates for the various types of cyclones. So what did we say here about limit of detection? We have to sample, modify these methods in such a way as to optimize the limit of detection so that it's no higher than 25% of the PEL. The PEL's 50 micrograms per cubic meter. So we have to have a limit of detection that's no greater than 12.5 micrograms per cubic meter. Okay, where do we get this limit of detection information? The OSHA ID 142 method actually gives us a detection limit in the proper units, because they've already done the math for us based on an 8-hour sample at the intended flow rate. Okay, so it listed as 12 micrograms per cubic meter. That meets the 12.5 max. Barely, but it meets it. Okay, now let's take a look at NIOSH 7500. What does it tell us? Well, the rest of these methods only give us the detecting limit of the laboratory analysis. Okay, according to NIOSH 7500, if you analyzed by X-ray diffraction, you have a detecting limit of 5 micrograms of silica. Okay, that means that it can't see 4. Okay, the least it can see is 5. NIOSH 7602 by IR sees down to 5 micrograms. 7603, which uses IR, sees down to 10. Look at the two MSHA methods, P2 and P7, 20 micrograms. Okay, what's the difference here? We have OSHA 142 that uses X-ray diffraction, NIOSH 7500 uses X-ray diffraction, MSHA P2 uses X-ray diffraction. Just for a moment here, compare NIOSH 7500 to MSHA P2. They both use X-ray diffraction, but one of them lists a detection level at 5 microns, the other at 20. Why is that? Okay, the NIOSH methods have been updated over the years. Every few years, they go through them, they update them as new information comes along. Those two old MSHA methods there were written years ago, 30 or 40 years ago. And if I remember correctly, they are tied to a federal register and probably can't be upgraded. So what they're reporting is the limit of detection of an X-ray diffraction spectrophotometer that was available 40 years ago. And that's the difference in these. The instrumentation has improved, and they have lower detection limits than they had years ago. So you can kind of play a game here with these. Sorry, I lost that page there. But you can kind of play a game here with these. If you want to use X-ray diffraction, it would be wise to have in your paper trail that you are following NIOSH 7500, and you request from the lab, I want these analyzed according to NIOSH 7500. So that's on the paperwork all the way through the trail, because then you've got this lower detection level. If you are stuck with the MSHA, if you're under MSHA and you're stuck with those methods, a couple of things here. You might not even be under this OSHA Silica standard if you're under MSHA. But the other thing is, what you need to do in those cases is get the lab to report the detecting limit on the lab report, because it's probably going to be better than that. And then you've got an argument that you have a better detecting limit. But how do we get from this 5 micrograms, and just looking at method 7500, how do you get from 5 micrograms to a microgram per cubic meter number? Let's take a look at what we do here. The limit of detection for the lab method is listed in these sampling methods. And again, you should always ask for that limit of detection to be stated in a lab report, so that you have the actual limit of detection that the laboratory is capable of giving you. But to get to this statement, no higher than 25% of the PEL based on sample air volume, we have to put sample air volume into this equation. So if we take that 5 micrograms that method 7500 tells us that their X-ray diffraction spectrophotometer can reach, and divide it by our sample volume, and in this example I've used 1.7 liters a minute and 8 hours, which is using a Dore-Oliver cyclone for 8 hours, we get 816 liters of air, or 0.816 cubic meters of air, and do the math, dividing the 5 by the 0.816, and we come up with a limit of detection for that method 7500, of 6.12 micrograms per cubic meter. Okay, if we do that to all the methods, these are the results we get in this, as this table shows here. So we're following 7500 or 7602. We're in good shape. We're well below 12.5 micrograms per cubic meter. So we're well below the limit of detection that the OSHA standard says we have to meet. Okay, that's sounds real good. You can do that with a Dora Oliver cyclone. You can do that with one of the cyclones you've been using for years. Okay, and you can meet that obligation. But what if you can't get an 8-hour sample? What if your sample is only 4 hours? What if the task is only 4 hours that you're sampling? And you're only getting a 4-hour sample. What does that do to that number? It's going to double it. And you're going to be up at 12.24, and you're going to be mighty close to that 12.5. And if your sample, if you're trying to take a 4-hour sample and it turns out to be 3.5, you're not going to make it. Okay, so this is when we need to think about using a higher flow rate cyclone. Again, if you're following one of those two methods and you can sample for 8 hours, you're there with a Dora Oliver. For shorter samples, you need to go to a higher flow rate cyclone. What would that 4.2 liter a minute cyclone do to that number if we're following method 7500? I don't have a slide that shows that, but it would more than double the volume in an 8-hour sample. So it would take that detecting limit down to about 3 micrograms in an 8-hour sample, and it would be about 6 for a 4-hour sample. So you'd be way in. So you might be ahead just starting out with that cyclone if you're not sure, or if you're dealing with a higher lab limit of detection than 5 micrograms. So you're kind of playing a game here. You're kind of you know, you have to look ahead. You have to think ahead. You have to see how long is the sample going to be. Can I get by with this cyclone? This Dora Oliver? Can I go to this 4.2 and be safe? Fact is, if you use the 4.2 all the time, you're probably going to be covered, you know, 95% of the time. It's only when you get down to 1-hour samples or 2-hour samples that you're going to have to go to that higher flow rate, that 9 liter a minute cyclone. And the fewer times that you go to that, the fewer complaints you're going to get from people that have to wear it, because it is big and heavy. So in review here, let's talk about the things we've just talked about. What do we need to do in this air sampling? Well, we must have a large enough sample to obtain a maximum limit of detection of 12.5 micrograms per cubic meter. That is 25% of the 50 that the PEL says. And we do this by optimizing methods and instruments. Okay. The methods call out cyclones. So how do we optimize? How do we get to a lower detection level? Well, you go to a bigger sample, and so you got to go to a bigger cyclone. So that's what that's telling us. We must follow one of these 6 methods that are listed. We can only use X-ray diffraction or infrared spectrophotometry in the lab. The lab must meet some minimum specified QA requirements, and there's a bunch of them. There's probably 30 or 40 bullet points in that Appendix A that tells you line item by line item what the laboratory has to meet from a QA standpoint. It's very specific. Okay. We always want to observe the cyclone flow rate for the cyclone we're using to make sure that we're using the right flow rate for the 50% cut at 4 microns. We want to be following the ACGIH curve. We always want to use a constant flow control pump, one that will hold the flow rate at within plus or minus 5% of where we set it. Okay. And the other thing that we learned here, if you use a medium flow rate cyclone, you can meet that detecting level for just about any 4 to 8 hour sample and still have something comfortable to wear. If you get down to a 1-hour sample, you're going to have to go to that bigger cyclone. And that's pretty much what we can get out of this Appendix A, and that's pretty much the guidelines that we need to follow. Thank you for this time, and let me know if there are any questions.
Thanks, Ron. Yeah, I guess one question came through is people want to know whether or not they can use an impactor.
Oh, that's a good question. I would be very careful there. The 6 methods that we're following back here, these 6 methods all call out cyclones. None of them call out an impactor. And the statement that we had to follow here is that we can optimize. It does say that we can optimize the methods and instrumentation to obtain a qualitative limit. Now, I don't know if that means changing the technology. I kind of doubt it by optimizing, because it's telling us that the optimization is based on air volume, if you read the whole statement. So I think we're limited to cyclones and to just going to a larger one. If someone is really wanting to use an impactor, I'll tell you, being an old school guy, I would get something in writing from OSHA on their letterhead and with a signature on it that says I can do that, because I have been, in my own experience, on 2 different occasions, I have been in court and trying to defend my data. And if you get an expert witness on the other side and you have veered from the method, boy, you're out there all alone, let me tell you. It's good to stay with what the methods tell you to stay with.
Okay. Someone was curious how ND results are treated. Are the silica components added at 0 or at the analytical limits of detection?
They're going to, for a non-detected lab sample, they're going to come back and say if their detecting limit is 5 micrograms, they're going to report it as being non-detected less than 5 micrograms. So you know, in a lab situation, and in the past life, I have been a laboratory assistant manager. But in a lab situation, there's no such thing as 0. You always have to report a non-detectable sample as being less than what you can see. And this is why I'm saying you should ask for that detecting limit on a lab report, because you might not get it unless you do have one sample come back non-detectable. Then they'll state it. But it would be a good idea, since this standard is telling us to sample, you know, to a criteria based on the limit of detection. We probably should have that stated on their lab report, and you may have to ask for it to get it.
Okay. Just kind of review question. Somebody asked if we were going to have a recording of this. Yes, we will have a recording. And then there was some curiosity whether they can get ABIH credits for attending this. Don't believe we set it up for that, so unfortunately we can't do that. See if any other questions are coming through here. Well, someone threw in as a FYI, respirable PPI impactors available from the companies such as SKC state that the samplers meet the criteria for OSHA final silica rule. So we threw that in. Let's see. How about the results of the quartz ND 0.01? Lost it for a second. 0.01 milligrams per meter cubed, and cristobilate. What is the silica result? Result, actually, I guess quartz, and cristobilate. Is there a silica result to that?
Well, yeah, I don't know. I don't know the answer to that. I'm not sure I follow that question. Quartz, of course, is silicon dioxide, so it is another form of silica. And I'm not sure how to answer that. So I'm going to guess.
Okay. Sure. In terms of the limited detection, are you aware of any literature that provides a little more explanation or the references to this or to the new standard?
No, unless it's been a while since I've read those NIOSH reports on the cyclones. I don't remember if they address it or not. But I don't know of anything on that. I mean, it's limit of detection. I mean, you can get information from from standard textbooks on laboratory limits of detection, what they mean.
Okay. This one's a little more of a product specific question regarding the Gillian, the BDX2. And the instruction booklet states the pump is not designed for use in low flow modules, is not recommended for use with cyclones or impactors that are required for constant flow control.
Yeah, the BDX2 is, I had mentioned that there are some really inexpensive pumps on the market that are designed for the asbestos abatement industry, and that's one, and it does not have constant flow control, so it's not going to compensate. In sampling for asbestos, you really don't need it, because if you're collecting enough dust on a sample to start choking the pump down, you're not going to be able to read the asbestos under a microscope. So you've got way too big a sample. So we normally don't run into issues like that, and the asbestos industry is always a bid process. So you, as a manufacturer, you have to come in with a very cheap pump in order to win any of that business. So the BDX2 is our version of that, and other companies have got them too. But that's why constant flow control in personal monitoring pumps was invented for cyclones. That's the thing you got to remember. So it's very important when you're sampling with a cyclone to have a pump that does have constant flow control.
Okay. Question about sampling. Would it be better to sample for the full 8 hours, even if you know the task will only last for 4 hours, or just sample during that task time?
Well, that's a good question, and it's probably one of semantics.
Yeah.
I would certainly, whatever your sampling situation, I would sample long enough to make sure that I've got that I've met that detecting limit with the equipment that I have. But in reality, you would be diluting your sample. Although the sample, the PEL is based on an 8-hour time-weighted average, so I guess you're really not cheating if you're sampling for 8 hours on a 4-hour task, because that is the 8-hour exposure for that person. So it's probably okay to do that, as I think about that. Yeah, I think, and you might want to call and talk to OSHA about that, but I think that since that is an 8-hour time-weighted average, and that is that person's 8-hour exposure, that's perfectly okay to sample for 8 hours if that particular task is only 4 hours.
Another little product specific. Do you recommend using the Giller Plus for higher flow applications like silica?
The Giller Plus is fine for the regular cyclones. What I recommend for that 4.2 liter a minute cyclone is to go all the way to our 10i pump because of the back pressure capabilities. The 5 liter pumps that are around, the Giller 5, the 5000, they have varying degrees of back pressure capability. But if you're sampling at 4.2 liters a minute, you're getting close to the envelope on those pumps, and you can start the sample with a clean filter with no problem. But as you sample and collect dust on it and the back pressure increases, you could, with those pumps, especially in a heavy dust situation, get to a point where they're going to fall out and not keep sampling. Where if you were sampling with a very powerful pump like the 10i, you've got all kinds of room. It'll keep on sampling long past where these other pumps would fall out, and that's any brand of 5 liter pump. In these cases, it's better to go with the overkill.
Okay. Any issue using a 25 millimeter cyclone as opposed to the 37?
Yeah, I don't ever recommend a 25 millimeter because a 25 millimeter cassette has got half the area of a 37, and it's going to double the back pressure. Whatever you've got on a 37, it's double when you use a 25, and back pressure is our enemy when we're sampling for dust. So I would never, ever, ever myself recommend 25 millimeter cassette for a dust application.
All right, good to know. Going back to the ND results, silica standard covers quartz, cristobalate, and tridimate combined, but how should ND results be added? I don't know if that's clarification from the previous.
The PEL is as silica. It doesn't specify how you got to the silica. So I don't think that it affects it at all, because the lab is going to report back silica. It's not going to report, it's not going to report back differently for quartz. It's just going to report back, crystalline silica from a lab point. Crystalline silica is crystalline silica. We have different, traditionally we've had different TLVs and for these things, but from a detection standpoint and from a non-detection report standpoint, I don't think it matters. And if somebody has a strong point of disagreement for that, please contact me later and let me know where you're coming from.
Okay. Actually, that's about it for the questions that we had coming in. A lot of good questions. So
they were excellent questions, and
yeah.
Some of them kind of difficult.
Yeah. Well, and I think everyone's trying to figure this out and what's going to work best, and might be a little trial and error as we go here. But
absolutely.
But no, we very informative. Hey, Brian, could you go to the last couple slides just real quick?
Yeah.
Yeah. So if you are, again, if you're interested in seeing the recording of this, you can find this on our website at rayco.com. We have a training page there, so we have a lot of our other webinars available there. We've also got a blog. You can follow us there, LinkedIn, Twitter, and also go to our YouTube page too. So we'll have both a recording of this, and then we'll also have the slides as well available to you. So give us a couple days, and we'll have those up. Next month, we're going to do a webinar on improving remote worker safety. So if that's of interest, take a look at our website. You can sign up for it. Similar deal. If you're not able to attend, we will have a recording of it. So thanks so much for joining us, Ron. We really, really appreciate you taking the time. It's a great topic, timely. We may have to review it again here in a few months if we have some other suggestions or inputs or best practices that are out there. But in the meantime, if you have any other questions, feel free to email me at tom@rayco.com. Hopefully we can point you in the right direction. And if not, we'll let you go. So thanks again, Ron. We really appreciate it.
Thank you, Tom, for the opportunity.